Figure 1 shows a central vertical cross-section, ABCD, of a paddling pool that has a circular horizontal cross-section. Measurements of the diameters of the top and bottom have been taken to estimate the volume of water the paddling pool can contain. So we've got 2 and 2.36. Using these measurements, the curve BD is modeled by this log equation. We're asked to find the value of K. So what's happened here is we're going like splitting this in half and just creating this curve on the right-hand side. And then in a minute, we're going to be doing a volume of revolution around the y-axis. But first up, let's work out K. Well, we can sub in the values. So I know when y is 0, that x is 1. Therefore, 0 equals ln 3.6 minus k. And it's ln 1 that's equal to 0, so k must equal 2.6. You could alternatively do e to the 0 and then do 3.6 minus e to the 0. That will give you, again, k is 2.6. Find the depth of the paddling pool according to the model. Yeah, because we don't have this, we know that this value here is going to be 1.18, but now we want to work out that. So I can just use our equation now, just with k replaced by 2.6. So y is going to equal ln 3.6 times 1.18 minus 2.6. If you put that in your calculator, it ends up being 0.4995. And I rounded that to 3 significant figures, 0.500 meters, so essentially half a meter. Okay, the pool is being filled with water from a tap. So it's coming in, it's filling up. And we're asked to find, in terms of h, the volume of water in the pool when the pool is filled to a depth of h. Okay, nice. So we're not looking to integrate up to the very top. We're going to be integrating along the y-axis from 0 to h. Now let's just imagine we create a little cylinder. Actually, it's not going to be that because it's going to be like this. And then we create a little rectangle, and then the cylinder is actually here. So our cylinder would be pi x squared, and then it's going to have a tiny little height dy. And then we're going to be summing all of these up. And that is where our volume of revolution formula comes from. Now we are integrating or summing up from 0 to this time like a variable h, which is quite unusual. We normally integrate, finding the volume of all sorts of things, chess pieces, jugs, bottles, spheres and things. But in this case, it's going to be a variable. That's absolutely fine. Now, the only thing we don't know is x, because we're not going to be putting this in. We need to make x the subject. So if we have y equals ln 3.6x minus 2.6, we can now make x the subject. 3.6x minus 2.6 will be equal e to the y. And then x will equal e to the y plus 2.6 over 3.6. I'm ready to sub that in. Okay, we've got everything in place now. So I'll bring the pi out of the integral, and I'll also bring out, I'm squaring the x, so x squared is just going to be this squared. Let's bring out the 3.6 squared, and then I'm integrating from 0 to h e to the y plus 2.6 squared with respect to y. Okay, at some point I'll work out what 3.6 squared is. But multiplying this bracket out, I'll get e to the 2y, then 2.6 times e to the y, but another one, so I'll get 5.2 e to the y, and then plus 2.6 squared, which I'll just leave as that for the moment. Okay, let's integrate. We'll get a half e to the 2y plus 5.2 e to the y plus 2.6 squared. In fact, I'm going to work out what that is at this point. It's 6.76. And then y. Let's also find out 3.6 squared. I think in the mark scheme they might have even left it in terms of 3.6 squared, but let's 12.96. Okay, and now I'm going to sub in h. So we'll get a half e to the 2h plus 5.2 e to the h plus 6.76 h. And then I just need to also put 0 in and subtract. So I'm going to be minusing a half, because it's a half times e to the 0. And I'm also going to be minusing 5.2. And then that 6.76y becomes 0. Okay, and we can't really simplify this greatly. Just a little bit, bring the constants together. So a half e to the 2y plus 5.2 e to the h plus 6.76h minus 5.7. And that is the volume of water in terms of h. Okay, and then to finish, we are given that the pool is being filled at a constant rate of 15 litres every minute. And we're asked to find in centimetres per hour the rate at which the water level is rising when the depth of the water is 0.2. Now, often in maths questions, they make the units quite nice. You don't have to worry about converting. Here, they do the opposite. It is like really awkward. Let's just remind ourselves what things were measured in to begin with. Because to be honest, when I do these questions, I do not pay attention, and it's kind of this actually tripped me up, and it's reminded me, you know what? Just make sure you're getting the units right. So h was in meters, and time is not actually in our equation so far, but it's coming in here every minute. But we want it in hours, so there's a bit to do here. 15 liters. Now, 1 liter is 1,000 centimeters cubed, or 1,000 milliliters. A milliliter is a centimeter cubed. So this is going to be 15,000 centimeters cubed every minute. But we want things in terms of hours. So I'm going to be actually timesing by 60 here. 15,000 times 60 is going to be 900,000 centimeters cubed every minute. But remember, in the model, the depth is in meters, so I need to change it to meters cubed. 1 meter is 100 centimeters, of course, but when you come on to meters cubed, it's then 100 cubed centimeters cubed. Apologies if you know this and you're like, yeah, I've done this loads of times, but just trying to explain where this comes from. Imagine you've got a 1 by 1 by 1 meter cube. It would be 1 meter cubed, but you need now times each of your three dimensions by 100 to get it in centimeters. That's why we're cubing it. So what we need to then do is take our 900,000 and divide it by 100 cubed. And that'll be meters cubed sorry, it should have been every hour before. And if we figure that out, we get 0.9 meters cubed per hour. So our units are consistent now. We've got we've got this rate in meters cubed per hour. So we want to find the rate at which the water level is rising. This is going to be dH by dt. And at the moment it's going to be in meters per hour because that's the unit I'm working with. And here we use a connected rate of change using the chain rule. It's going to be dH by dV times dV by dt. Now that is what I was just figuring out on the right. It's 0.9. Okay, and that's why you've got to get it because V was in terms of H, and remember it was in meters. So all we got to do now is find dV by dH, sub in 0.2, and then take the reciprocal. Going to get pi over 12.96 e to the 2h plus 5.2 e to the h plus 6.76. Then when h equals 0.2, that's in meters, dV by dH ends up being, put this in your calculator, 3.5398. So then this here is going to equal 1 over 3.5398. And we get 0.2542 meters per hour. We're nearly there because actually we're asked for centimeters per hour. So we just times boot through back by 100 and it's 25.4 centimeters per hour. Okay, that is the rate of change of the height at the instant when the depth of the water is 0.2. We've got this constant volume, but because the area, cross-sectional area is changing, then it changes how the changes the rate of change of the height as the water level increases. Good question. Volumes of revolution, we've had to do some rearranging. We've actually worked out a volume in terms of a variable. And at the very end, we've dealt with a connected rate of change to work out the rate at which the water level is rising. Well done on all these questions. Keep going.